All right, guys, I'd like to do just a couple examples with you just to look at elliptical motion and what we can do. And again, like I said, we'll be able to do a lot more when we have rotational motion. We can do conservation of angular momentum and then energy, conservation of energy, because both energy in these systems and angular momentum are both conserved. So you'll see some multiple choice we can't answer yet, but I thought that it was worth introducing the center of mass and introducing some of these problems, and then we can build off them when we get to that section. All right, so the elliptical orbit of a comet is shown above. You can see it's nice and squished, very eccentric. Positions 1 and 2 are respectively the farthest and the nearest positions to the sun, and position 1 is a distance 10 times that of position 2. What is the ratio of F1 to F2? All right, so F1, these are the same masses. So I'm going to have G. I'll have little m for the comet, big M for the sun. Seems fair. So I'm going to have G, little m, big M over R1 squared is equal to G, little m, big M over R2 squared. And we should be able to cancel out a number of things. So I have 1 over R1 squared over 1 over R2 squared. I could rewrite this as R2 squared over R1 squared. And so that would be 1 squared over 10 squared, which would be 1 over 100. So this is the same as that. Remember, with the fraction on the bottom, you can invert it and multiply. A spacecraft is placed in a circular orbit around a planet with a mass that's known. So here's our spacecraft up here. So we know the mass, we know the height. What additional information is needed to calculate the speed of the spacecraft in orbit? So we would need, we have the force, we have the F net, we don't need the spacecraft's mass, the little m. We do need 1r. We have this. We know that because it's a constant. So do we know what r is? No. We know what h is. R is actually going to be the distance from here to here. And so we don't know the radius of the mass. So we need to know the planet's radius to figure that out, to get the whole distance on there. Our rocket lifts a payload upward from the surface of Earth. The radius of Earth is r. The weight of the payload on the surface of Earth is w. The force of the Earth's gravity on the payload is w over 2 when the rocket's distance from the Earth is. So we're going to say that weight is gmm over r squared. I want to solve for r, right? I want to get r. I want to get r by itself. So I'm going to flip the positions of r squared and w. And so r is going to be equal to radical gmm over w. All right, so what I do when they ask me questions like this, they give me a situation, they put me in a new situation. Anything that didn't change from situation to situation, I put in a 1 for it, even if I know what the value is. So I know this is 6.67 times 10 to the negative 11, but that's a mess. So I'm going to put in a 1 for that. So I'm going to have radical 1 for G. Is the mass of the rocket going to change? Hopefully not noticeably. They didn't give us enough information for us to actually deal with that burning fuel. So I'm going to say no. Is the mass of the planet, is Earth, going to change? No. They're telling us that the weight is going to go from being W to W over 2. So that's going to be changing from 1 to 1/2. So this is the factor that are changed by, and so I'm going to have 1 over radical 2. I'm going to have 1 over radical 1/2, which is the same as radical 2 on the top, right? I can flip this up to the top. So it's 1 divided by 1/2, which is 2. So this is going to be radical 2. All right, an object of mass m on a string is whirled with an increasing speed in a horizontal circle as shown above. When a spring breaks, the object has a speed of v naught, and the circular path has a radius r and a height h above the ground. Neglect air friction. Determine the following, expressing all answers in terms of h, v naught, v, and g. The time required for the object to hit the ground after the spring breaks. This is going to be a horizontal launch problem. So actually my y direction. In the y direction, my v naught is 0. My acceleration is g. My displacement is going to be h. I can either make it h or I can make it negative h, but then I need to make g negative g. So I don't have a negative underneath it. I'm going to say that x minus x naught equals v naught t plus 1/2 at squared. Cancel that out. I'm going to have 2 times x minus x naught over g is equal to t squared. I'm going to use their letters. So it is radical 2h over g. And if I made g negative and h negative, I would end up with the same thing. The horizontal distance the object travels from the time the string breaks until it hits the ground. So it's moving at v naught. So in the x direction, v naught is v naught, v is v naught, a is 0. I don't know x minus x naught, but I know that my time is radical 2 over hg. And so I'm just going to have v naught t, because a is equal to 0, right? So the 1/2 at squared is going to cancel out. So this is going to be v naught radical 2h over g, which agrees with this. The speed of the object just before it hits the ground. So in the y direction, this is 0, this is g, this is h, this is radical 2h over g. I can get the final velocity in the y direction. So this is going to be g times radical 2h over g, which I can rewrite. This is, g is just the square root of g squared. So if I put g squared inside of there, and then I can just simplify this to 2hg. So I'm going down with the velocity of 2hg, but radical 2hg, and I'm going to the side with the velocity of v naught. This is our true velocity. And so this squared is going to be equal to 2hg squared plus v naught squared. So v is going to be equal to the square root of 2hg plus v squared, which is what I agreed to. The positions shown in the diagram, I have tension, and I have big mg. So it's being, the angle they give us is this angle. All right, so I'm gonna look at my components of T. So this is gonna be T cosine theta, and this is gonna be T sine theta. The y direction is gonna be easy because F net's equal to 0. It's only accelerating the x direction. And so that's going to be T sine of theta equals mg, right? Ups minus downs equals 0. X direction is going to be trickier. So I have F net equals m v naught squared over r. And again, I want to use their letters. So where v naught is our initial velocity, big M and big R are what they use. The force is T cosine theta. All right, I'm going to have to use a trig identity that you might not have learned yet. But so what we have, if we look at our triangle, is we have T going this way. We have Tx going this way, which is this T cosine of theta, which we're saying is m v naught squared over r, and the other one we have is mg. So we know that the relationship is the Pythagorean theorem, that a squared plus b squared equals c squared. So t squared is going to be equal to m v squared over r squared plus mg squared. And so t is going to be the square root of m squared v to the fourth over r squared plus m squared g squared. And then it looks like I factored out an m, because both of these have an m, so I can take an m to the outside. And so this is v to the fourth over r squared plus g squared is our answer. That's a mess.